Excellent, thank you. So in the next talk, I'm excited to tell you about the Nautilus Space Observatory. So this is a space mission concept and related technology development that we have been leading at the University of Arizona now, but for 6 or 7 years. This project really started about 7, 8 years ago when I went to a Northrop Grumman workshop. It was a very small workshop. Northrop Grumman's then vice president invited a small group of experts and tasked us to spend 3 days debate and figure out what the future of space telescopes look like. And so there was one thing we all agreed on, that we don't have an answer to that at that workshop. We all thought that it's probably not going to be just simply a larger James Webb. It will have to be something very different. There was a feeling that we may be reaching the limits of the current technology. And from that workshop, I actually got to chat with the Northrop Grumman chief engineer, and we realized that we are thinking very similarly about potential for different architecture paradigms. So that's how the project started. I was very fortunate here at the University of Arizona to find some of the world experts in developing large optics, diffractive optics, which turned out to be absolutely essential for this project. So here, let me mention that I'm leading the astrophysics space mission concept development side. Tom Mills there, professor in the optical sciences, College of Optical Sciences, is leading the optical design, and Daewoo Kim is leading the alignment metrology component of this project. And we are aided by a large team of enthusiastic students and postdocs and scientists within the University of Arizona. That's where more core team is, but we have members from Northrop Grumman and then also scientific contributors from elsewhere too. We have been receiving generous funding from the Moore Foundation and from different units of the University of Arizona that made this work possible. Okay, so without further ado, let me tell you about what our goal is. It is to characterize 1,000 Earths, and what we need to do for that is to change the paradigm in which we build space telescopes. So you may ask the question, we just launched James Webb, which is an incredible space telescope. It works so well. Why do we think that we may need to change the paradigm? And so let me just give you a couple of numbers. It is now estimated that for the next flagship, which is currently maybe the Habitable Worlds Observatory, we may need to spend about 30, maybe 40 years building that telescope. And the expected increase in the diameter of the telescope is maybe 0 meters. Maybe it will be the same size as James Webb. Hopefully we can push that a little bit further, but it is not going to be a very significant increase. It will be in some ways optically more capable, but in other ways it is not going to be a bigger telescope. There is also a concerning number, right? James Webb was in part so expensive because it was a unique prototype which had about 170, if you count it differently, maybe over 300 single point failures. The team did an amazing work navigating through those failures, but part of the cost is to make sure that not one of them actually fails. You may think if something would have failed on James Webb, we know how to do it. We could build a second James Webb, but that's actually not the case. Most of the team members are no longer working there. They work on other projects. The facilities cannot reproduce anymore what they were able to do 15, 20 years ago. So it is a unique facility in its current shape. So on that side, the technological side, there is something that may be an indication of a plateauing technology. On the science side, there are great demands for the kind of telescopes we would need. And so here I just put 2 numbers. I will not go into details here, but when our goal is to understand Earth-like planets, we have to know that we are looking at very complex systems. In fact, it's systems of systems where abiotic processes, climate feedback cycles interact with an ecosystem that we may not know anything about. So how do you understand a complex system? The main thing you need is data. But the current technology is pretty much limited to delivering data on a relatively small set of planets. So there is basically this technological challenge, and then there's a scientific challenge. And this, I think, combine into also an opportunity when we look at what's happening on the space launch industry side. So this is just a figure. There are many such figures that show space launch costs. How much does it cost to get a kilogram to orbit, going from 1960 to 2020 and beyond. And what the main thing you notice is that for many decades, this was basically scattering around the constant value. It has decreased already by an order of magnitude, and it is set if SpaceX is successful or competitors are successful in going down by another factor of 10, maybe even 50. So that's a complete game changer. We will be able to not only get to orbit cheaper, we will be able to get to orbit much larger masses and at much higher cadence. SpaceX is, with Starship, is aiming to launch every week. Well, they may not reach that goal, but it is nevertheless orders of magnitude better than what we can do today. So I'm sure you have all seen this image that gives, of course, a sense of progress on the SpaceX side. I would say that it's not just SpaceX. There are competitors out there on the smaller launch capabilities. They are already catching up. And on the larger side, I think this demonstrates the feasibility of getting to orbit much lower cost, much faster. About 6 months ago, there was an article in Science. It was a well-researched article from a journalist, Sarah Scholes. Basically, the statement was, Starship is the largest rocket ever. She asked the question, are space scientists ready to take advantage of it? The article was pretty negative. It said that basically we are still building space telescopes like we did in the 1980s and 1990s, and on the biggest scales, we are not appreciating the changes that are happening. So I will get back to that. So basically, I showed you that there is a technological revolution in launch vehicles, and of course, we can talk more about this. On the other side, we have grand challenges in astronomy and planetary sciences that need larger apertures. We want bigger telescopes, and we don't want to wait 30, 40 years for those. So connecting these two basically is a new technology. We need a new technology. We need a new paradigm to make use of these opportunities. And we believe, our group believes, that new technology that will enable progress is scalable optical manufacturing. In a sense, replacing the way the optical telescope assemblies for current telescopes with a design, with the technology that is quicker, cheaper, lower cost to build, test, integrate, and operate. So let me get back to the key goal. So I'm primarily motivated by really a science goal, and that science goal is to understand Earth-sized planets, Earth-like planets, and then understand potential ecosystems that may exist there, at least to the level that we can recognize them. And my personal motivation was that I feel, and has been that I feel that if we end up building 30 years a mission that can characterize 5 or 7 planets, we will not get a conclusive answer at the end. We will be left with uncertainty. So I formed this team initially, and that has been our goal ever since, is to come up with a technology that will enable us to study 1,000 exo-Earth planets. So to do this, I mentioned that we need a paradigm change. It's just not conceivable that the current technology could come anywhere near. We need lower cost, lower risk, and a highly redundant platform that we think can be now built on Space 2.0 opportunities. Just for those who are interested in the exoplanets, we are going to use transit technique instead of high contrast imaging. This is the technique with which we have discovered all the Earth-sized planets as of now, and with which we have been getting the most information about their atmospheres. This is a very scalable technology. You don't need super high optical quality. What you need is basically lots of photons. This is a simulation. All of this is published, so I can refer you to the paper in the Astronomical Journal. With transmission spectroscopy during transits, we have already demonstrated in space the stability that's required within a factor of a few to reach basically the precision we need to detect biosignatures. The only thing that we don't have currently is a large enough number of photons. So if you had a large enough light collecting power, and you don't see the critical number here, but these simulations assume that we have a 50-meter diameter space telescope. With that, you could study 1,000 planets and search for biosignatures. Of course, that sounds crazy. We cannot build a 50-meter space telescope, but we don't actually have to. We can collect light in other ways, in ways other than building one giant telescope. So what we do in Nautilus is basically currently concept development and technology development. We have made enormous progress in technology. I will show you some of the highlights. We have developed a concept. We have actually developed a series of concepts because we will need to build stepping stone missions as we go to the larger sizes. Our goal is to fit that mission into a flagship category mission, and we have done 3 different cost estimates, and all of them suggest that we have a reasonable chance of reaching that. So we have a team of about 15 with multiple inventions, patents, 20 publications, a series of prototypes, funding from the Moore Foundation. And this is really a University of Arizona project. Going forward is what will remain, but we have, of course, participation and interest from other partners too. This is one of our really the key piece of technology. What you see here, and I don't have time to go into the details, but the key goal here is to replace primary mirrors and the optical telescope assembly and all the stability that exists for that with a hybrid lens technology that can be replicated and via molding. This has been a very mature technology in the commercial space. If you look at the top of the line Canon and Nikon lenses, they no longer use conventional refractive lens bodies and groups. Instead, they are using diffractive lenses. These lenses remain very thin, even when scaled up to large diameters. So you can create very large diameter, yet very thin, very lightweight lenses that are very insensitive to misalignment. So that makes everything downstream in the optics much cheaper. And we can create these basically with optical molding. So in many factories, you can routinely get thousands of lenses in a day. And even in research settings, every 2 hours in smaller scale, these lenses are produced. So we have invented a new type of lens. This didn't exist before. That is extremely well suited. It was developed for space applications and provides the highest image quality, broad wavelength coverage, replicability that we need. Let me show you what we envision, how this could change how we build space telescopes. Hopefully it won't be too loud. It is. So we would be launching with a SpaceX Starship. And we would be launching not one telescope, but many identical units. Each of these would have a cost category. We could do 2 SpaceX Starship launches. We could build up to 35-unit telescopes, distributing costs, distributing risks, providing much more capability to the community. We estimate about 75–80% of the science that currently is done with Hubble or James Webb could be done with this telescope constellation. It's not a formation flying interferometer. These are independent operating telescopes. But when you need the combined light collecting power, telescopes could all turn to the same target and observe, for example, an exoplanet transit, providing you a light collecting power equivalent of 50-meter telescope. That's what you see here. So while this looks pretty radical, really the only component that we don't have at hand is the front optics. This is the hybrid lens that we have been developing here at the University of Arizona. Everything else has space heritage. So where are we now? So we are focusing, we have concept development. I'm not sure that this works anymore, but I will just speak loud. So we have been focusing on space mission concept development. We have made progress and published multiple papers on that. But the key progress really was on technology development. So we went basically from coming up with a concept, getting a target identified for the technology, to the point that we have been able to make progress along basically most key components. So, so basically here sorry, grab this. Go ahead. So basically what you see on the top is that we have science case, optical design, molding machine, diamond turning, prototype, optical testing, alignment integration, and thermal vacuum tests. And on the different rows, you see the diameters. We started small. We have basically accomplished everything we wanted on small scales. We transitioned to the medium scale, where we are almost complete with most of the components. We have a pending proposal for thermal vacuum testing for this size lens. And then we are going to then transition to a 1-meter capability. What I want to know that all of this has been published, lots of experiments here. But the key thing here is that the most expensive component is the diamond turning machine to create the mold in metal that we are using for the glass molding. Amazingly, unfortunately, it turns out that there was a major defense funding and push for that. So that actually exists, and we don't need to reinvent that. We just need to use demonstrate the surrounding technology. Sorry. So I will just say that the key components results have been published. In the optical side, it has made quite a splash. I think it didn't quite really propagate to astronomy yet, the astronomical community. We have been presenting this at the SPIA. This is a double session with 8 talks, invited talks on these, all aspects of the technology. And basically our vision here is to develop a statistically robust assessment of habitable exoplanets and search for life, along the way changing really how we do space astronomy and planetary sciences too, develop a new paradigm for lower cost resilient and multi-purpose space telescopes. We are planning to build a stratospheric demonstrator for our current technology and then work on a MIDEX Pro Plus mission proposal as the opportunity opens. UA has a critical role here. We invented the technology. We are developing the capability for replication, for alignment, integration, as well as the scientific leadership. So I think just wanted to go back to these questions. Are space scientists ready to take advantage of this? I think most of them are not, but I think we here will be. Thank you. Sorry for breaking this.
Yeah. I'm not sure where you went to get that. No, it's back up to maximum.
No, I know what this was.
Yeah,
So
no, I checked it that way.
Check that. Okay.
Can you hear me now? All right. Yeah. I'm just going to max this. All right. Any questions? Yes.
One of the thank you. I think it seems like one of the biggest challenges will be to in-flight challenges will be to maintain the stable configuration of all the components. So, what is the timeline at which you expect to have your stable configuration of all the components looking at the same direction? For how long and how accurate that can be, and how challenging is that particular part of the process?
I don't think we. Okay, so the question was what are the constraints on the alignment and the configuration, the formation flying? So that's a good question. Actually, this is not formation flying. The relative position of the telescope doesn't matter at all. We are not combining the light with phase information. It's just intensity measurement. So it doesn't really matter at all. In terms of the precision, we need basically positional precision, but this is actually very similar to what was already demonstrated. It's pretty similar to what's demonstrated by telescopes that are observing transiting planets, from Kepler that has demonstrated 2 parts per million to Hubble and James Webb, which are basically an order or they are approaching within an order of magnitude the precision that we need. So we don't actually think that that's going to be a challenge.
Thank you.